they couldn't supply this closed source driver on their product, so we at SUSE had we had this driver update process where we provided means so that you could download the driver from the website of the from ATI, but we couldn't ship it with our product. Basically, due to the fact that it loaded a kernel module which was closed source into a GPL kernel, which violates the GPL, so we would have been in big trouble if we had provided it on our CDs or whatever. And so it was kind of dissatisfactory for both sides, consumer users and also for Linux distribution. But both sides put pressure put pressure on ATI to change the situation. Now users usually are very vocal in public and express their dissatisfaction about the situation publicly. Now Linux distributors, mostly technical partners of ATI, they don't give the public advice to their partners, but behind closed doors, of course, there were discussions going on. Another thing that appeared, I think, was last year was the Vivo driver, a project where some people in this room were involved in. Daniel Stone. Daniel? Where's Daniel? Okay. Jerome? Jerome in here? There's Jerome. It was the attempt, pretty successful attempt even to reverse engineer what the closed source catalyst driver and the BIOS does to initialize the hardware. So it was basically a mode setting driver that helped to overcome this problem. And it also was kind of serving as a means to put some pressure on the ATI. I was saying that, well, we're doing something with the need necessarily don't need information, so we can do our own driver. This was aimed at R5XX only at the time, and when the R6XX generation came out, there was virtually nothing. There was no driver that could deal with it. There was no open source driver, even inside. And also the Catalyst driver, at the time of the release of the hardware, the closed source proprietary driver by from ATI, was not able to support this hardware under Linux. It supported it under Windows, of course, but not under Linux at the time when the hardware was released. That was kind of also for AMD, the company that purchased ATI, a way to look into this situation. AMD actually had a very long history with open source drivers and supporting the community in writing drivers for AMD hardware. So it's different. AMD has different paradigms, and so this kind of helps to change the entire situation. We at SUSE had a long history of good relationships with AMD because we kind of started with the x86-64 project. We did the port of Linux to x86-64, which was a very successful product. And since then, we have a pretty close relationship to AMD. So AMD came to us and asked us what our ideas were to create an open source driver here. So three of us, Matthias, Nick, and me got together and put together a proposal how this could be done. Different steps involved there. point in there was to have community involvement early on, so release something pretty soon once the first bits are there. Somebody would have to do the first bits and then go and share them, and so that people can jump in. Another thing that we asked for was that documentation for the chipset is available to everybody very early on. Oops, I should have put it in the presentation mode. Press the button sometimes. Without any strings attached. There used to be, at certain times, there used to be a program for open source developers where they could sign an NDA to get documentation from ATI. I think this is kind of messy for both sides. ATI needs to keep track of this, and actually we wanted to avoid this. So this was our proposal, and then AMD asked us to jumpstart a driver, create an initial driver that can then be released to the public together with initial set of documentation. So I think it was around mid-July, we got the first drop of documentation from ATI, which at that time was still under NDA because it required some cleanup or it needed to be looked over. And we started to write this driver. Okay, so before I talk about the details of the driver, I think John also already had transparency on this, so I can be brief on this. Yeah, John has a diagram of the different components that are involved in graphics, and he had three components outlined. One was the driver inside the X server. Currently, the X server contains a driver that is basically the mode setting, which does 2D acceleration. We have two different architectures in the X server right now. One is the old X386 acceleration architecture, which now there's Daniel, one of the people involved in the Vivo.
So what?
Which has been around for, even before X386 4.0 was released. So it's pretty old. It basically accelerates the core X protocol. There's not much or pretty much nothing to accelerate any new functionalities, any new rendering functionalities like in the X-Render extension. Then we have EXA, which is newer and supposed to help to accelerate render. It doesn't do so much acceleration of the core protocol anymore because this is not that often used anymore. So, a lot of drivers support both architectures because XAA is considered the more stable, more reliable one. XA the more experimental one, and in many benchmarks, if you see benchmark results, you still see that XAA is still a little faster than XA. I'm going to go into the details so much on this. So I think John went into this already. We can do this on radio hardware. We can do this either through classical analog programming or using the command processor. Another thing that the X driver does is set up the DRM. Basically, it this currently, this is the current model. Actually, we are looking into a new model using a kernel-based memory manager. At the moment, the eich server, the driver in the eich server is still in charge of allocating memory buffers. All this allocation is very static. If all this is done inside the eich driver. Another thing that the driver does is context switching between 2D and 3D applications, because you need to have a different hardware state, and this is also done in the eich driver. Well, another thing that's classically been done in the eich server is to program video overlay scaler to support Xvideo. Now, this is something that we don't or can't do anymore in Radeon HD, but we'll get to this later. Well, the second part is a kernel module, the DRM module, which basically submits command buffers to the hardware. Does hopefully not all do this. That's the basic command checking, so that no illegal commands get to the hardware, because once you can do this, you can have a graphic chip do all kinds of wacky things on your hardware. And it also takes care of interrupt handling. The third piece is actually the DRI client-side module. It's a sub-module that gets loaded by the libgl when you run the 3D application. It pretty much converts the OpenGL stage to hardware-specific commands. And today, with Scalar, contains the backends of assemblers and not Scalar shaders. Contains the backends assemblers and compilers for those shaders. So, here, to understand the next slide a little bit better, I used a graphic that I picked off the ATI website. I hope this is okay, John. I'm using this graphic. It's not very detailed, not completely accurate. It describes most of the parts that we have been programming in the Radeon HD driver so far. So, just to give an overview, here's some parts missing. Here you would have first the memory sequencer, or the surface engine, which reads out video data. Here's scan line data from the frame buffer, and also the PRTC, CRT controllers, which provide the timing information, provide the timing signal, and are driven by the PLLs for the pixel clock. Is also not in here. The data that comes out of there gets then fed through the display pipeline. The gamma correction, color correction. This is what we do in the color lookup table. Then, further down the pipeline, you have a scaler, which can rescale the image if your screen, like on laptops, has a different physical size than the image of the frame buffer you want to view. This is the scaler engine. Now, here is something drawn in. There's the video overlay engine. This is something which we will probably not use ever, because the overlay engine does not, at least on R5XX and R6X, does not have a scaler anymore. So you could overlay video data in YCRCB and some YCRCB formats, but you can't really scale it to the size you want it. So whatever video you would have, you have in the original size. So this part is probably never going to be used. Further down is an output crossbar, which We have two independent CRTCs and two independent memory sequencers, so we can have two sets of data from your frame over running through the display engine. And here in the crossbar it gets distributed on the different outputs. Now, today if you look at your video card, you mostly have two jacks on the back. Oftentimes they're both DVI jacks, most of them. Depends on most of DVI jacks provide two signals, one analog signal for the old monitors with a connector like this. There's an adapter which you can plug in here, and also a digital signal for digital panels, mostly digital monitors. So you have analog DAC outputs for normal CRTCs, or analog input monitor digital outputs for DVI, CMDS outputs. You have, it's not on here, you have LVDS for panels, snap panels on laptops. And also you have television. Most cards, I think most API cards today have TV out. So all these different kind of outputs and how these two signals get to these outputs is controlled by a crossbar. Actually, there's a TV encoder which, when you hook up a TV, does some funky rescaling of the data so it fits your TV norm. Actually, we don't have much documentation on this part, or not any documentation at all, so this is pretty much a black box for us. So the picture is not completely accurate. It seems to be that you can assign this to both tracks. Okay, wait. There we are. Okay. So, what's the present status of our Radeon HD driver? Well, we can pretty much do full mode setting. We can support most of the outputs. Now, TV out is not completely done yet. We've got most of the pieces coded up, but we can't control the TV out, the TV controller you've seen on the previous slide yet. We will be able to control this probably through Advise. I will come back to this on a later slide. But not all the pieces for this are in place yet. We can drive all kinds of digital outputs. We can drive DVI. We can drive panels. We have support for XRNR 1.2. Pretty much standard today. We have support for XAA, both XAA and XA. At least for our 5XX, you've probably heard from John's talk that on our 6XX or any later generation after our 5XX, the dedicated 2D engine is gone. Instead, you would have to use the 3D engine. Now there's emulation in the later hardware, which pretty much emulates the 2D engine, but this needs to be initialized, so the state needs to be set, and the code for this is not yet in the driver, so we don't have that yet. I expect, the code for this will probably be in the T-Core that's going to be released, so we can plug it up there and do 2D acceleration also for our 6. what we've done in the driver very early on, we looked at the different subsystems you've seen on the previous slide. We separated them out in software. I mean, if you look at the older X drivers, everything was somehow clumped together and was just a huge pile of mess, because the original kind of X drivers usually, or the design that's been used was just for one single output per card. So the first step, what we did, we separated off, or wrote separate subsystems for all the different hardware pieces, separate systems for the PLL, for the CRTD, the surface engine, the sequencer that reads the data from the frame buffer, for color transformation, for the outputs. We separated all of them, the DAC for analog, the LVDS for panels, and the TMDS for DVI, and HDMI. We also have support to abstract out the connectors, the physical connectors, because you can have a situation where you have different outputs connected to one connector. This is the case on the DVI dual, where you have analog and TMDS on one connector. But you can also have, another thing you can have, one output shares several connectors, which is the case between analog VGA connectors and TV out. They usually use the same DAC, so an abstraction layer, to have an abstraction of the connectors here is very helpful. From there, using this separation and abstraction of the different subsystems, we looked into how to map this onto XRNR 1.2. So we didn't go into XRNR 1.2 and try to map the hardware directly. We first separated out everything nicely in software, and then checked how we can interface this into the abstraction model of the XRNR 1.2 extension, or XRNR 1.2 mode setting system. This kind of helps because whenever new engine or whenever new hardware comes around which changes any of these subsystems, it's very easy to plug this in. And also, the hardest thing in driver development, especially in graphics driver development, is to get the bit banding right, especially when your documentation kind of sucks. So writing up those pieces is probably the biggest work. The infrastructure on top is also a lot of work, but it doesn't change that much. There are not that many generations, hopefully. So it's a good idea to have those pieces reusable. So when you change to another environment, you can carry those along. So it's kind of nice to have them abstracted out. A lot of the old drivers don't have this, which makes it very painful to adapt to. New models like the XRNR 1.2 came along. One of the really old drivers. It's really painful to plug things apart and stick them back together so that it fits XRNR 1.2. So we extracted out these things very much from the beginning so that we are very flexible here. Well, another thing, of course, not a big deal, cursor engine. Support for I2C to read out EDC from the display. This is all separated out in different subsystems. Also, we added software abstraction for monitors. Now, something like this is also part in XRNR 1.2. We found that we needed to do some more and some different validations than XRNR 1.2, so we put a layer on top of this. But this is completely a software abstraction. Another thing, we have well, John talked about it already, and we'll have to talk about this on a later slide too. We have a layer for atom bias that deals with the bias caused and data tables in the bias. So this separation really proved to be very useful, very flexible, so the integration of R and R1.2 proved to be very simple. Now, our initial driver didn't support R and R1.2 right from the outset because we first wanted to get all these different submodules right, and we just plugged them together, somehow hard-coded to get some modes up and see how this works. And later on, we integrated this into the R1.2 model. So, also, the design is very portable, so we need to separate between driver private parts and hardware-related functions and interfaces to the other parts of the X server into the device-dependent EDX card, or even the calls directly from DIX, from the device-independent layer of the X server. Sorry?
You plan to incorporate on exchange the EDX rather than
It's possible. There was somebody asking just a few days ago on the mailing list if it was possible to port the driver to, what was the operating system called? Zozo or something? Yeah. It's clearly another open source operating system I've never heard of. And I think if we take all the bit banging pieces out, you can take them, port them over to a completely different environment. And also, whatever you do, people talk about kernel mode setting, you can take all these pieces out and plug them someplace else.
Sure, but I'm just confused about the separation between stuff that goes into the CPU and stuff that goes into the DDS. Because K-drive is the only other DDS that actually really works, and even then it's really complex.
And maybe I misunderstood what I was referring to. It's just mainly the abstraction between a driver level, low-level function, and anything that interfaces above layers. Because you don't want to have DDS functionalities way down inside your bit banging pieces. Because if you want to port it someplace else, you would have to change all the whole thing. So yeah, I'm not sure if anybody would want to port this to K-drive. I don't know what the status of K-drive is at the moment. Is there anybody actually still working on it?
Yeah.
Okay.
Only on embedded.
Right. Oh, like you guys have. Are you going to use API hardware? Probably not.
No.
Okay. Okay.
Who knows? You will be seeing more and more APIs, embedded. API hardware embedded in system chips that are coming, and that will be probably targeted by K-drive server. So, it could be interesting to have those things, cases, abstraction cases, be shared across different media.
I think what very few people know is that another area where HI is pretty strong in is providing hardware for embedded devices. John may know more about this. John?
We're kind of early stuff.